Hello friends, welcome to the series of lectures of Mathematics 1. Myself Hardik Patel from LJ Institute of Engineering and Technology. Up to last session, we have seen the basic concept of Fourier series such as Fourier series with a period 2 pi, Fourier series of discontinuous function, change of interval and Fourier series of even and odd function. Today's topic is Fourier series of half-range Fourier series. That means Fourier half-range Fourier series we are going to define. Now, what is the half-range Fourier series? If you are going to define the Fourier series on interval 0 to L, then it is called the half-range Fourier series. See, basically you have two type of half-range Fourier series. First one is a half-range Fourier cosine series, which is defined on interval 0 to L, and it is given by fx is equal to a0 by 2 plus sigma n running from 1 to infinity an into cos n pi x upon L, where a0 is given by 2 by L 0 to L fx dx, and an will be 2 by L 0 to L fx into cos n pi x upon L dx. See, sine and cosine, we have two types of series. If you are going with a sine series on same interval, then it is given by fx is equal to sigma n running from 1 to infinity bn into sine n pi x upon L, where bn is given by 2 by L 0 to L fx into sine n pi x upon L dx. Okay. Now see, if you are going to find the sine and cosine series for the same function, then you will get the both of them here. In even and odd function, we have either a0 is equal to 0, sorry, a0 and an is equal to 0, or you have bn is equal to 0. But here the interval is a half interval. Total length of interval is L. Okay. So in this case, we are finding the cosine series as well as sine. We can find cosine and sine series for the same function. Okay. So please remember this thing. Now we are going on to the example. So find the half-range sine series of the function e raised to x on interval 0 to capital L. So first of all, you have given the sine series. That means the Fourier series fx sine series is given by fx is equal to sigma n running from 1 to infinity bn into sine n pi x upon L. Correct? Where bn is given by 2 upon L 0 to L fx into sine n pi x upon L dx. Now small l is now capital L, so here we have written a capital L. Correct? Because see, in a half range, wherever your interval ends, that is your L. That means here it is starting from 0 ending to capital L, so small l is going to be a capital L. So wherever we have the value of small l, at that time we are going to replace it with a capital L. Please do not compare it with a 2L. Okay? This is a half range, so your interval is a half interval, and if it is half interval, then you have to compare small l with whatever the end value of a interval. Okay. So now fx is nothing but it is e raised to x. So if you are going to put the value, then you will have 2 by L 0 to L e raised to x into sine n pi x upon L dx. But e raised to ax into sine bx has a formula e raised to ax upon a square plus b square, a sine bx minus b cos bx. Okay. So here a is equal to 1 and b is equal to n pi x upon L. Sorry, n pi upon L, capital L. So integration is going to be 2 by L e raised to x upon 1 square plus n square pi square upon L square into the bracket a is 1, so 1 into sine n pi x upon L minus b, that means n pi by L into cos n pi x upon capital L, and limit is from 0 to L. Now substitute the limit. So first simplify this term and substitute the limit. That will give you, here we are going to take the LCM, so L square will going to be in the numerator, and that will give you 1 L will be cancelled out. You will get 2 of L upon n, L square plus n square pi square, and put the limit. So e raised to L into the bracket L. If you are going to put L here, then L will be cancelled out. Sine n pi has a value 0 minus cos n pi. Okay, cos n pi upon L. So you will have minus n pi by L into cos n pi. Minus, if you are going to put 0, then e raised to 0 into this term sine 0 has a value 0 and cos 0 has a value 1. So you will have minus n pi upon n. Done. Now simplify these terms. That will give you 2n pi l upon 2n pi upon l square plus n square pi square. See, this l came common out, n pi common out, and that will give you minus e raised to l into minus 1 raised to n plus 1. Now this is the value of Bn. Put it in a half range series. That means your series is fx is equal to n running from 1 to infinity, sigma n running from 1 to infinity, Bn into sine n pi x upon capital L. And Bn has a value 2n pi upon L square plus n square pi square into the bracket minus of e raised to capital L into minus 1 raised to n plus 1 whole into sine n pi x upon capital L. Okay. So this is the Fourier series, sine series of a function e raised to x. Now we are going on to another example. Find the half-range Fourier cosine series for fx is equal to sine x and interval is from 0 to pi. Now see, if you are going to start with an interval 0 to pi, then L is equal to pi, correct? So small l is equal to pi, that is the first thing. And if you are going to write the Fourier cosine series, then the cosine series is given by fx is equal to a0 by 2 plus sigma n running from 1 to infinity an into cos n pi x upon L, but L is pi, so pi will be cancelled out and you will have an into cos nx, where a0 is given by 2 by L is pi, so 2 by pi 0 to pi fx dx. Fx is a value sin x, correct? So you will have 2 by pi 0 to pi sin x dx. Sine has an integration minus cos and limit is from 0 to pi. So substitute the upper limit and lower limit. That will give you 2 by pi into minus of cos pi minus cos 0. But cos pi has a value minus 1 and cos 0 has a value 1. So you will have 1 plus 1, that will be 2 into 2 by pi, that is a 4 by pi. So this is the answer of A0. Now same manner, if we are going to find the an, then an will be 2 by pi 0 to pi fx into cos nx dx. N pi x upon L, but L is pi, so pi will be cancelled out and you will have cos nx dx. So now if you are going to put the value, fx is sin x. Now sin x into cos nx. Here you cannot directly apply u into v. That means you cannot integrate this by integration by parts. So multiply this 2 inside. That will give you 1 upon pi integration 0 to pi 2 sin x into cos nx. That means you have 2sc. 2sc is s plus s. So you will have 1 upon pi 0 to pi sine of x plus nx. X common out. That will give you sine of 1 plus n into x. Plus sine of x minus nx, that will give you sine of 1 minus n into x dx. Now integrate this term with respect to x. So you will have 1 upon pi sine 1 plus n x as the integration cos of 1 plus n into x divided by 1 plus n. And sine of 1 minus n into x divided by, it has an integration minus of cos 1 minus n into x divided by 1 minus x. Now substitute the upper limit and lower limit. So if you are going to put the limits, then you will have minus of cos 1 plus n or pi divided by 1 plus n minus cos of 1 minus n pi divided by 1 minus n minus, if you are going to put 0, then you will have minus cos 0 upon 1 plus n minus cos 0 upon 1 minus n. Now you are aware of cos of 1 plus n into pi, that will be a cos pi plus n pi. But cos alpha plus beta is cos alpha cos beta minus sin alpha sin beta. And sin n pi has a value 0, cos pi has a value minus 1, and cos n pi has a value minus 1 raised to n. So this is going to be a minus times minus 1 raised to n. Same manner, cos of 1 minus n times pi is going to be a minus into minus 1 raised to n. So put this both values here and simplify. That will give you 1 upon pi into the bracket minus 1 raised to n upon 1 plus n plus minus 1 raised to n upon 1 minus n minus minus 1 upon 1 plus n minus 1 upon n minus 1. Here common out minus 1 raised to n and take LCM. That will give you minus 1 raised to n into 1 minus n plus 1 plus n divided by 1 minus n square. Here also take the LCM, so you will have minus into minus of 1 minus n, minus of 1 plus n divided by 1 minus n square. Simplify these terms, that will give you minus 1 raised to n into 2 upon 1 minus n square minus minus 2 upon 1 minus n square. So minus minus plus 2 upon 1 minus n square can be common out. So that will give you 2 upon pi into minus 1 raised to n plus 1 divided by 1 minus n square. Now the first thing you have to remember that here you cannot put n is equal to 1. So please remember, whenever you are going to integrate, then you have to put the condition n must not equal to 1, because the denominator is going to be 0 in that case. So this is the particular case in which you have n is integer, either 1 or 2 or 3. In that case, this denominator is going to be 0. So it is 0 for n is equal to 1. And that's why this an has a value, this value other than n is equal to 1. So for n is equal to 1, we have to find out the separate value. So if you are going to find the Fourier series, then first of all, fx is given by a0 by 2 plus sigma n running from 1 to infinity an cos nx. But you have to find a1 separately. So we are writing this series in a form of a0 by 2 plus a1 cos 1x plus sigma n running from 1 to infinity an cos nx. So now we are going to find the value. So for n is equal to 1, we are going to find n a1 separately. So a1 is going to be 2 upon pi integration 0 to pi fx into cos nx. But n we have taken 1, that means it is cos x dx. Now put fx is sin x. So you will have integration 2 by pi integration 0 to pi sin x into cos x dx. Now multiply this 2 inside and you will have 2 sin x cos x. But 2 sin x cos x has a value sin 2x. So your integration is reducing in the form of 1 by pi 0 to pi sin 2x dx. Now sin 2x has an integration minus cos 2x by 2 and limit is from 0 to pi. So if you are going to put the limits, then you will have 1 upon 2 pi into the bracket minus cos 2 pi plus cos 0. See 2 common out, cos 2 pi plus cos 0. Cos 2 pi has a value 1 and cos 0 has a value 1. So minus 1 plus 1, that means you have a1 is equal to 0. So this is the answer of a1. Now put this value, all these values in half range cosine series. That means your cosine series is now going to be of the form fx is equal to a0 by 2 plus sigma plus a1 cos x plus sigma n running from 2 to infinite an cos nx. A0 has a value 4 by pi, a1 has a value 0 and an has a value 2 by pi into the bracket minus 1 raised to n plus 1 divided by 1 minus n square into cos nx as it is. Now simplifying this term, that will give you sin x is equal to 2 by pi plus 2 by pi into, put n is equal to 1, n is equal to 2, n is equal to 3. So 2 by pi into the bracket minus 2 by 3 cos 2x minus 2 by 5 cos 4x plus minus 2 by, if you are going further, then you will get minus 2 by 35 cos 6x and so on. Now minus 2 common out, and that will give you sin x is equal to 2 by pi minus 4 upon pi into 1 upon 3 cos 2x plus 1 upon 15 cos 4x and so on, so on. So this is the half range cosine series of the function sin x. Okay. So these are the topics which we have covered today. Here we have given some example for practice. So please do it yourself. And if you have any doubt or any queries regarding these topics, then please feel free to contact me. Thank you so much.